Okay, it's 3:31, so let's start today's class. In the previous class, I introduced about this course, and then I briefly introduced what computer architecture is. So this is the computer architecture course for undergraduate students. So you need to understand what will be learned in this course. Also, you need to set a goal for this course. So that's also important. So I know this is a mandatory course for computer engineering and computer science students. So I believe many students selected to take this course because this course is a mandatory course. But that means this course is very important. Also, as a computer engineering or science student, you need to know about the computer systems because the computer engineering is not learning about programming or coding. It's coding. Computer engineering means it's learning about the computer system and then the research on how to make a good software and good hardware. That means computer systems. So it's very important to understand about the computer systems. Okay, so in the previous class, I think you can see this slide. Okay, so in the previous class, I just showed some the various figures of computer systems actually. So as you can see, this is also computers. These are computers. So actually, this computer is different from the general computer processors. So if we mention the computer systems, that means this computer system equips a general processor called CPU, a central processing unit. But recently, many computer architecture researchers focus on some specific type of processors called domain-specific architectures. So I believe the most famous domain-specific architecture is GPU, or graphics processing unit. And then I know, yeah, most of you already know about the GPU. This because this is very hard recently due to Bitcoin, maybe. Yeah, okay. So I into some questions. So you need to know why we need to learn about computer architecture or computer systems. So this is a basic step to understand computer hardware. So why do we need to understand about the computer hardware? Because it is required for making better computer systems. The better computer systems means what are better computer systems? So I believe I already explained in the previous class. So what is a better computer system? If we want to purchase new computer systems such as new desktop or new laptop computers, so what will you why do you want to use a new laptop or new desktop or new smartphone? It's also applicable. So what is the better computer systems? Okay. Yeah, it's a good answer. So better performance, as I mentioned, better performance and low cost. So higher performance than the old desktop or old laptop computers. Also lower energy cost or power consumption cost. So it's also true for if you want to purchase a new smartphone. So if you want to buy a better smartphone, better than the old one, so you need to check the performance of your new smartphone. Also, you can check the what is that? It's a learning time. So that means the battery performance or the usage time of the performance, usage time of the smartphone, because smartphone runs using the battery. So it need to consume the lower energy. So we first check the performance and cost for new hardware. So this knowledge is required for making better computer systems. But some of you have a some of you, I believe some of you want to become some good software engineer or as good programmers. So is it required also? So is it required to learn computer systems for programmers or software engineers? The answer is yes, because this is a mandatory course. But this knowledge for computer system hardware or the interface of software and hardware of the computer system is also necessary to software engineers or programmers, because this knowledge is required for making better software. That's obvious. Also, so as I explained, mentioned the domain-specific architecture, this domain-specific architecture required some specific knowledge on the this specific hardware or specific architecture. So as a software engineer, you need to understand how to use this specific hardware or specific processors. So for example, if you want to make a GPU code, so I believe some of you heard about the CUDA programming or OpenCL. So this CUDA and OpenCL is required to run codes on the GPU. So actually the GPU is designed for parallel processing. And then in order to run your application on these GPU processors, like for parallel processing, then you need to learn how to code with the CUDA or OpenCL. But in order to write the code with the CUDA and OpenCL, you need to learn about the specific hardware architecture of a GPU. Because the GPU is designed for specific domain applications such as graphics or image processing applications. This GPU has some specific hardware, has equipped the specific hardware component and its own software execution model. So you need to understand how the software is executed in the GPU hardware, but you also need to understand how the software is mapped to the hardware of GPU. So this knowledge is also necessary for these GPU programmers or some programmers in the specific domains. Also, if you want to create a better software or a better program, so that means also your program runs well on the computer, most of computer systems. So runs well means your software runs fast. So your software consumes lower energy. So this aspect is tightly connected to the goal of hardware design for computer systems. So I said better computer system means higher performance or low energy cost. So also that is also applicable to the software design. So better software means this software runs fast or smoothly, also runs well. That means related to the performance of software. Also, in order to get the good performance with the software, you need to understand how to use the hardware resources or some hardware components of computer systems. So it's related to the computer architecture knowledge. Also, low energy. So most of our software runs on the server computer systems or desktop or mobile computer systems. That means smartphones. So that means you need to also consume low power or lower energy to run your software. So it's related to the hardware also. So that means you need to also understand how the energy is consumed in the computer hardware. Also, the power is consumed in your smartphone or server systems. So it is also required for better software design. Okay, so what you will learn in this course? What will be learned in this course? So first we will learn how programs are translated into machine language. So actually in this class, in the today's class, we will learn about abstraction of computer systems. So I will explain later, but so when you program when you write the program code with program languages such as C, C++, or Python, Java. And actually, this program language is similar to our native natural language, like English, actually English. So, but I said these high-level languages are not understandable to the computer systems. So computer systems just understands digital numbers or digital code, such as it's a binary code, 0 or 1. So that means our high-level languages should be translated into the machine code. So we will learn how this translation happens in the computer systems. Also, we will learn about the hardware and software interface. This is called the instruction set architecture. And then we will learn about the performance of computer systems. So this is also important. And then this is the also the I said this the three important topics in this course is the instruction set architecture and pipelining and memory hierarchy. So we will for the memory hierarchy and the pipelining, we will learn how to design better computer hardware. So we will learn about the pipelining to improve the performance of the processor. Also, we will learn about the memory hierarchy, how to efficiently use the data in the memory systems. Okay. So this is I read the some topics we learned in the previous class. So now I will teach about the abstraction of the computer system. So what is the abstraction? So in this slide, you can see the very cute kid, and then I think he was she. So this kid is trying to drive a car. So it's not safe, but just for some comic photo. So let's just that you try to drive a car. Then, so what should you learn about the car? What? So what is the knowledge, what is the required knowledge to drive a car? Okay. So in order to drive a car, we need to learn how to adjust handle, so it's for direction. Also, we need to understand how accelerator work, also how brakes works with so these pedal. So we need to learn about the accelerator pedals and brake pedals. Also, we need to learn about the gears. So is this knowledge enough for driving a car? Yeah, so yeah, but let's focus on a car, not the law or some so driving law or some infrastructure or environment of some driving. So just to focus on car. So in order to drive a car, so that's actually basic knowledge, the basic knowledge for driving a car. So just how to use a handle, how to use accelerator or brake pedals, or how to use gears, just several knowledge in the car. But inside of a car, we know that the system of car is very, very complicated, very, very complex. So we are not mechanical engineers, so we don't know about the inside of a car, but in a common sense, we know that inside of a car, there is an engine. So there is a very complicated systems that control this engine or brake systems or wheels. So it's a very complicated actually. So as normal people, we cannot make a car, so we don't know about the inside of a car. So because this car system is very, very complex. But as a driver, as a normal driver, we don't need to understand about the inside of a car, these very complex systems. As a driver, we need to know several knowledges about the handling, pedals and gears, some other several knowledges. So what does that mean? It means car system is very complex, but this complex knowledge or complicated systems are not revealed to drivers. That's an analogy of abstraction. Okay, let's see the another analogy. So this is a vending machine, and then this is a customer. So in order to use this vending machine, so what should we know? So required knowledge for using this vending machine is to just push buttons for the corresponding product. And then also we need to insert coins or credit cards to the vending machine. That's it. And then just push button. But inside of a vending machine, this vending machine is also composed of some embedded machines or embedded computers. Also, the embedded computers learns programs. Also, there are some mechanical systems inside of a vending machine. But as a customer, we don't need to understand about the inside of a vending machine. Also, the programs running on the embedded system inside of a vending machine. Also, we don't need to understand about this embedded systems inside of a vending machine. So this is just a secret. So this knowledge is not revealed to the normal customers. So as a normal customer, what we need to know is to just push button and insert coin or credit card, and that's it. It's another analogy of abstraction. So what does that mean? So if abstraction means that, so abstraction means if it's an upper layer, so like a customer or drivers, if upper layer people do not need to know about this complicated or complex lower layer, then these complicated systems or mechanism of lower layer is hidden to the upper layer people or some upper layer systems. Then, but we need to know about the minimal knowledge between the upper layer and lower layer. So what is this knowledge? To a car, for the car system, the required knowledge is how to use handle, pedals, and gears. Also, for the vending machine, the required knowledge is push buttons or inserting credit cards. So that's a interface between higher layer, upper layer, and lower layer. But this complicated or complex systems of lower layer is hidden to the upper layer. Just the required interfaces are revealed to the upper layer. So abstraction means that this, if knowledge is not required to know, then this knowledge is hidden. But just the required interface knowledge is revealed to the upper layer. Okay. So this is very complex. Then it's very hard, it's difficult to understand. So if we need to know this very complex and difficult knowledge to drive a car, then a very small number of people can drive a car. And then that is actually disaster. So in order to make most of the people can drive a car, then we need to make a very, so this knowledge is hidden. And then we make a very simple interface. Then these simple interfaces are revealed to the customers or drivers. So that's on abstraction. So let's see some several layers of a computer system and the abstraction in the computer systems. So I copied this figure, the digital design and computer architecture textbook. Then I think actually this digital logic design course used a different book, but when I taught digital logic design, I used this book, digital design and computer architecture. So actually, the first chapter of the DDCA book, this book. So the first chapter is about the abstraction of computer systems. So abstraction. So as I explained, abstraction means hiding details when they aren't important. So you don't need to know about the detail of the lower layer because this is very complicated. Also, it's very difficult. You don't need to know. So, and then provide only required interface information between two adjacent layers. So what does that mean? So in the computer systems, I said there are many layers. So this figure shows the layers of computer systems. So in order to understand every layer of computer systems, it will take maybe hundreds of years for normal, except for normal people, because so in order to build this entire computer systems, we need a very low layer of analysis, such as the semiconductor or physics of electrons, or what's that? So physics, actually the modern physics of the electronics. Also, we need to know about the semiconductor properties. Also, actually, about this device knowledge, like a semiconductor device knowledge, we need to know about the analog circuit design, also digital circuit design, logic design, microarchitecture, blah, 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 blah. So we don't need to understand all aspects of these layers. So as researchers or some engineers, we just focus on the specific layer of computer system. So for example, as a computer architect, so, like me, the computer architect just focus on these layers, architecture and microarchitecture. Also some aspects of operating systems or drivers, like something like here. So we just focus on the architecture and microarchitecture of the computer system. And then in the digital logic design course, like COSE222, right? So you need to learn about this logic design. So, but as you can see, this logic design is the lower layer of computer architecture. So when we mention about the computer architecture, this detailed aspect of the logic design, such as the AND gate, OR gate, exclusive OR gate, is just ignored, because if we mention that is logic design or logic gate, then the computer architecture or aspect of the computer architecture will be very, very complex, or it's very difficult to understand. So we do not mention about some detailed behavior of logic design of the computer. It just handles the microarchitecture of the processor. So microarchitecture means that it's like a pipelining and then instruction fetch or something like ALU. So you will learn in this course. Also, we just handle the architecture. Architecture means that how to organize the memory system, or how to organize the processor and then other I/O devices, buses, and the entire computer system, computer hardware. So there are many layers, but when we focus on a certain layer, we do not focus on the detailed aspects of the lower layer, because that is very complex or difficult to understand. And then we just build the interface between layers.
어디야? 집. 오늘
Okay. Then for the computer engineer, this abstraction is very important. Also, as a normal engineer, this abstraction is also important. So when you make some product, then we just reveal the required knowledge to the customers or the people in the other department. Because so this is the just required knowledge, not some detailed knowledge is just hidden, because they can understand our detailed knowledge or some detailed aspect of the lower layer. So this abstraction is important. So let's talk how the program is executed on a computer system. So I believe everyone knows that computer systems or a computer is composed of hardware part and software part. Then if we focus on just the software, this software is revealed to the customers. So what is the example of the software? It's just applications such as the office programs or games running on our computer or smartphone. So those are software. Also, those software is called the applications. So this is called the application software. So actually, a user learns this application software, and then this application software interact with user through the I/O devices, right? So when you use Office software, we use keyboard or mouse, a keyboard or a mouse. So when you use play a game, the smartphone, we touch the smartphone touch screen. Also, we adjust the angle of our smartphone. So just these are the example of I/O devices. So that means the application software directly interact with users. Okay. So then how can we create, or how can we generate these application software? Sometimes it's called just applications. So these applications are written in high-level languages such as C, C++, Java, or Python. So, but as this software runs on the computer hardware, this software also use the hardware resource of the computer systems. So as I mentioned, when we learn application software, we use the I/O devices. So these I/O devices are also hardware of a computer system. Also through these I/O devices, we control resources of processor or computer systems. So that means the hardware also should be controlled by software. So what's the problem? This is the hardware, but so it's very hard to understand about the detailed operation of the hardware, because we just use the C, Java, Python, and then we don't know about the detailed hardware operation of the computer system. So we use the system software. So system software is the interface between application software and hardware. So this application software is friendly to the normal user, but so this hardware world is very difficult. So we cannot. It's very difficult. I said it's difficult to understand the aspect of hardware to the normal people, so customers, users. So there is a system software that interfaces between application software and this hardware. So these are the examples of system software. Is a compiler and operating systems. So compiler translate this high-level language code, the machine code. So like that, the computer only can understand the machine codes. And then operating system control the resources of hardware, such as the memory space or some processors or I/O devices. So to the application software engineer, this engineer need to learn how to write a code using high-level language. And then to the system software engineer, they need to understand how to control the hardware. But this application software can have a minimal knowledge on the hardware. Okay, you understand? And then hardware is just the processor, memory, and its I/O controllers. So this is just the hardware. So because the computer has this kind of layers, so and then we also focus on the specific layer of the computer system. So we don't need to understand the some detailed knowledge of the lower layer or some complex world. So I already explained about this program code, so high-level language, and I actually skipped this assembly language, but I will explain later about this assembly language in the chapter 2. So the high-level language is translated into the assembly language, and then this assembly language is also mapped to the this machine code. So as a software engineer, actually this machine code is very difficult to understand because the figure or the system of assembly code is very different from our natural languages. That's why we cannot understand about the machine code, or it's very hard to understand the assembly code. So we use the high-level language to create our application software. And then this application software is translated. So these are also other layers. So it's translated, and then this is the also assembly code. So assembly code is some specific code, and then composed of instructions and operands. And then these instructions and operands are mapped to the machine codes, like these binary codes. So this assembly code is generated from this high-level language code, and then this assembly code is translated into the binary code, and then computer can understand this binary code. So executed by hardware. So another layer. Okay. Okay, let's go back to the hardware, the processor. So this is the figure of Kaby Lake, it's a multi-core Kaby Lake CPU made by Intel. So this is the die photo, so die photo of Intel CPU. So can you understand how CPU work using this die photo? Because in this die photo, so actually you can see the all transistors, but you cannot figure out the detailed figure of the transistor because transistors is very small, and then there are billions of transistors inside of a single chip. So it's very hard, but this figure includes the every transistor inside of an Intel processor. But if you see that this figure, can you understand how processor work? No. Yeah. It's just a figure, so I think it's gorgeous. It's very looking good, but it's just a figure. So if you see that this figure, so about don't we can understand about the Intel processor. Okay, how about this figure? So in this figure, so this figure shows which part is assigned to which component of a processor. So as you can see, this area is assigned to the memory controller of a CPU, and then this part is the system agent. And also you can find that there are 4 CPU cores inside of this chip. Also, you can find, the GPU is included in this CPU processor, Intel CPU processors. Also you can find the level 3 cache. Also you can find the interconnection bus inside of a processor. So what is different from the previous figure? The previous figure just showed the entire image of the processor, but it's very hard. But this figure shows that which part is which component of a CPU. So if we see this figure, we can know that, this Intel processor has 4 cores, like 4 CPU cores here, here, here. So, this Intel processor includes the memory controller and GPU. Then we can know that this processor has level 3 cache, and that this level 3 cache is shared by these 4 cores because there is interconnection bus is between these cores here. So there is a system agent here. So if you see that this figure, you can understand more detail of the detailed aspect. So more detail of Intel processor. So this is another abstraction of the processor. We don't know. We just know how many cores are included, and then GPU is included. And if GPU is included or the memory controller is included in this CPU chip. So this is a kind of aspect of computer architecture, but this abstraction is also just shows the narrow knowledge on the Intel computer processors, right? It's not detailed knowledge. So my question is that, can you understand the process architecture? It's a process architecture is in Korean is a 구조. So process architecture means that how the hardware works, and then the hardware is organized. Using the chip model, we cannot understand because the knowledge is not revealed to us. And then another abstraction level. So this photo shows the another abstraction level of our Intel processor. So we can understand the some narrow knowledge of the Intel processors actually using this figure. Okay, so but we don't know about the detailed knowledge on the CPU core or GPU or memory controller. We don't know about the detailed organization or detailed architecture of the CPU or GPU in this figure. So abstraction helps us deal with complexity. With the abstraction, we just reveal the required knowledge to the people. So, and then also we can hide some detailed lower level knowledge. So also as a computer architecture, in the computer architecture field, we just reveal the instruction set architecture to the software world. So detailed hardware organization or hardware implementation is hidden to the software engineers or software world. We just reveal the interface between hardware and software. So this interface between hardware and software is the world of computer architecture. So there's a detailed implementation or digital design or analog design and semiconductor design is also hidden to the computer architecture. Okay, so for example, so this figure shows the block diagram or some more detailed architecture of Intel CPU. So as you can see, this architecture is composed of many rectangles, many blocks. So rectangle represent a block, so hardware block. Also, these blocks are connected each other because so in order to build a hardware, you need to design a single component, and then this single component is connected to other components. So component means the block of the hardware. So in this figure, you can find some hardware components such as the branch predictor, decoder, or it's hard to understand, scheduler, instead execution units. So EU means execution units. So, oh, what's this? You can find the flow of signals, like the signals from branch predictor to the cache, and the branch predictor to the what's decoded stream buffer. You can find, oh, what's decoder? What is execution unit? But as you can see, well, the signals flow from the cache, decoder, and then, oh, there are many operations. OP means operations, OP code. So these OP codes are provided provided to the what's this? Reorder buffer, scheduler, execution engine. What is the execution engine? What are execution engines? So you can find the ALU, multiplier, floating point. So what is this? It's a cache, level 2 cache. You can find level 1 cache is connected to the AGU and loading instruction. So these are the this figure shows the example of architecture. So as you can see, but you can find the many blocks and many components here. But I believe you cannot understand what this block means. But if you learn in this course, so actually, hopefully, at the end of this course, I hope you can understand about so it's block of this figure. So we will learn about the cache. So we will learn about the execution engines or ALU. We will learn about the decoder in this course. So we just learn how cache works, so how the decoder works, and then how the execution unit works. So I hopefully I hope you can understand some of these blocks. But in this course, we do not learn how these blocks are implemented. So this implementation is related to the logic design, digital design, or some analog chip design. So this detailed knowledge is hidden. So as you can see, but if you see this block, we can understand how this block works in the computer processor because we will learn about these blocks. Okay, but we just learn how this block behave or how this block work. Detailed implementation is hidden. Okay, so that's just some architectural view of the computer processor. Also, this is the abstraction of the computer architecture. Okay. So I explained about the architecture abstraction. I explained about the abstraction of the computer systems. So do you have any questions? So to summarize, we will learn about this level in this course. Okay, like this level, the operation of this block. Like this is some example, but we'll learn about the pipelining. Actually, this processor is also very complex, and then it's not a level of the undergraduate student, but like this diagram or figure, we will learn about some operation of each block here. Also, the connection between blocks like this arrow. Then we will learn about how to organize these blocks and connections inside of a processor. That is an abstraction level we will learn in this course. Okay. I hope everyone understands. Okay. Then, so this is the next topic of the discourse. So I will briefly explain about the components of computer systems. So I believe if you took a computer-related course in your high school, then I believe everyone learned about some components of the computer systems. So like out devices such as display, like monitors, also input devices such as keyboard or a mouse, it's a mouse. Also some I/O devices such as network card, network interface card like NIC. Also, I believe you learned about its processor. Processor is the brain of a computer system. So these are the components of the computer system actually. So let's see this figure. So this is the main board of the computer systems, like main board of a desktop computer. But actually this figure shows the very old type of mainboard of a desktop computer. So I copied this figure from the ASUS homepage. So this is the old generation of ASUS mainboard. So as you can see, you can find that this is the CPU socket. So if we attach the CPU to this socket, then properly, then the computer can run. Also, you can find many I/O ports, such as the this is the graphics card port. So actually, recently we used the PCI bus, PCIe. This is the PCI Express, but the old main board used the AGP port for the graphics card. Also, you can find several PCI slots here. So in this figure, you can find the I/O port for the keyboard and a mouse, and then it's a display port. Also, you can find these are the memory slots, like a DIMM slots. So if we put the memory DIMMs on this slot, then you can use RAM. Also, you can find the mainboard chipset. So these many I/O devices are connected to the CPU through these mainboard chipsets. Okay, so because this board is the old generation board, so you can find two chipsets in this figure. So actually, this chipset is called the North Bridge, and then this chipset is called the South Bridge. So through these chipsets, peripherals of computer systems are connected to the CPU. Okay. These are the simplified diagram of computer system that connects the CPU and many components. So, but as you can see, this is the computer system architecture of old generation. So this is the CPU, this is the memory, like RAM. So our data is stored in the RAM. Okay. So if you write the code such as the A equal 10, the C, then that means that this is the space for data. And then this space is specified by address. So that means that is some place in the inside of memory. So A equal 10 means that the data 10 is stored in the memory, right? So then CPU will compute the data stored in this memory, like C equal A plus B. So that means that the computer performs the add operation, like plus. So this add operation is performed inside of the CPU. So what is required? This data is transferred to the inside of CPU. Because the data is stored in the RAM, right? So in order to transfer this data to the CPU and memory should be connected each other. And then this connection is called the memory bus. Okay. So actually all the generation of the computer system, there is a nose bridge chip here, and then this nose bridge chip control the data traffic between CPU and memory. Also, this north bridge chip is connected to the south bridge chip, and then this south bridge chip is connected to the many peripherals and graphics card here. So, like this is the keyboard, or mouse, where this is the LCD, the monitor here. So the required data is transferred to the from memory to the monitor, like this. So this data is transferred to the other peripherals. But this is the modern architecture of the computer system. So actually, for the modern computer systems, the nose bridge part is included in the CPU chips. So actually, this nose bridge include the memory controller. So the data in the memory is connected to the CPU by this memory controller. So this part is included in the CPU chip. And then this CPU chip is directly connected to the graphics card because recently the graphics handles a large amount of data. So data transfer to the graphics card is very critical in the computer systems. So graphics card. So recently we used the PCIe Express bus to the graphics as a graphics interface. So this data transfer between CPU and graphics card is directly controlled by CPU chip here. And then the graphics card is connected via PCIe bus. Also, the memory is directly controlled by CPU. But that means this nose bridge part is just included in the CPU processor chip. Also, through this some DMI interface, the south bridge chip, this south bridge chip is called the mainboard chip, such as the X490. This south bridge chip controls the I/O devices of the computer systems. So the storage devices are connected to the South Bridge chip, and then the data in the storage is transferred to the memory and CPU through this South Bridge chip, like mainboard chip actually. Also, other devices are connected. The network is connected also. So this is the example of the Intel chip block diagram. So as you can see, you can find the processor here, main board chipset here, like G390. So you can find the USB port, network interface, audio and storage. So you can find the GPU interfaces. So you can find the DIMM interface like DRAM here. So this figure also shows the many components of the computer system, and then connections among various components in computer systems, right? So this figure shows the another level of abstraction in the computer systems, right? So if you see that these figures, then you can understand how the components and peripherals are connected inside our computer systems, right? Okay, so until now, I explained about the abstraction of the computer systems, processors, and then how components are organized and connected inside our computer systems. But I also explain various levels of abstractions in the computer systems. So you can find the different levels of abstraction, such as this figure. So this is the abstraction inside of an Intel processor. Also, you can find that this is some detailed levels of components inside of the processor, like a cache, execution engines, or decoders, branch predictors, and the other components. So you can find the detailed architecture of the processor in this figure. Also, this is another level of abstraction, like how the computer systems are organized between various components. So this is the processor and the peripherals, GPU, DRAM, and South Bridge chip or mainboard chips. And this figure just a very small part of this figure, like small core of this processor. So these are the different levels of abstraction. Okay. So okay, do you have any questions? So I think we don't have enough time to move on the next topic, like technology trend of the computer systems. So do you have any questions? Oh, so actually you can you can ask a question in Korean. It's possible. Okay. So 네, 팝 퀴즈 있을 예정입니다. So we will take pop quiz occasionally, not every time, not every class. MD. Where is MD? It is. So, sorry for my bad writing. It's a main board chipset. Actually, so it's an MB. It's a main board. Yeah. So I have bad writing. Also, I will briefly explain about the homework assignment. So actually, I post. It's not first. It's a zeroth homework. So actually, 0 points allocated to this first homework. So it's just a survey, not the serious homework. So I will briefly explain about the homework. So actually, I will post the homework questions on the Blackboard as a PDF format. So and then you need to submit your homework. You need to submit your homework result electronically. That means you need to upload your homework result, homework assignments on the Blackboard. So we did not receive any physical format of the homework. Okay. So you need to submit your homework with PDF format only. PDF, not. So we just use the PDF format only. Okay. So, okay, you can easily generate this PDF format file from MS Word or Hangul word processor. So that's easy, actually. Also, handwriting is okay. So, so actually, I will post the homework questions as a PDF format. Then you can find the questions on under this PDF file. But also you can save the you can write your answer with the handwriting. That's okay. And then scan your answer sheet as PDF format and then post to your this PDF file on the Blackboard. So you may think that, or you may say, oh, I don't have any scanners, but recently there are many good applications, actually mobile applications that scans your document very easily, like a Microsoft Office Lens. So these mobile applications can scan your writing using your camera, mobile camera. So if you write your answer using your handwrite, then you can scan your homework sheet with these mobile scanner apps, okay? And then generate the PDF file and then post this PDF file on the Blackboard, okay? I post the homework number 0. So it's not a serious homework. It's just a survey for this course. And then actually the 0 point is assigned to this homework. So even if you don't submit your homework for this homework assignment number 0, but you don't have any penalties, or you will not have any penalties, or actually the point assigned for this homework is 0. Okay, but this homework is I generated this homework to make you get familiar with this electric submission via Blackboard. Okay, so just to remember that you need to use the PDF format for this homework. And then we will not receive any physical answer sheets or physical format of the answer for this homework assignment. Okay. So any questions? 네, 수고 많았습니다. 네. So thank you for listening and then see you on Wednesday. Okay.